No, I'm not from your class, bro. Don't add me.
Who is this?
It's
Okay,
Sunnama.
okay, okay.
Yeah, okay. I think everybody is here. Yeah. Okay, I think the live body is visible to you.
Yes, sir.
Yes, sir.
Now, see, in the morning we have discussed about the properties of various components individually as well as mixtures. Once again, I just typed in a word file. Just we will go through once how these properties will look like, what are the notation schemes we follow, and then it is easy to derive various expressions. Okay, first one, consider in a system, you can see my word file, I guess. Is it okay?
Yes, sir.
Yeah. Now consider the system is composed of two components. Okay, as far as your syllabus is concerned, only two components are there. So which are we designate with component A and component B, as given here. You can see as given here. You can see component A and component B. Then for this mixture, if we consider this mixture component A and component B as a liquids first, then concentration of liquid is defined as mole per unit volume. Okay, concentration is defined as moles per unit volume. Moles has a units of mole per volume, mole per meter cube. Volume is meter cube. So mole per meter cube is equal to concentration. Then usually for the liquids, we define this mole per unit volume composition as density divided by molecular weight overall average. Okay, this needs to be average, rho by m average. We um, we used to define for liquids in this way. Okay, this is the notation schemes for the overall liquid. For example, consider the first property. First property is mass, which is a fundamental quantity. If you remember in the instrumentation and process control course, I just given you the five types of fundamental units and various types of derived units. Okay, you can I assume that you know what are the fundamental properties, what are the derived properties. Fundamental properties of there are five types: mass, temper, length, time, temperature, and mole. Mass, time, temperature, mole, and length. Okay, these are the five types of derived properties. Sorry, it's a fundamental properties. Whereas pressure and others like molecular weight, moles, these are all the derived properties. Okay, so mass is the fundamental property, which is denoted by mi. For the ith species, we will denote it as mi. Okay, whose units are kg in the SI unit. Then component, if this mass is associated with component A, then we will denote it with small m. Then for a total mixture, so system is composed of only two components, A plus B. So total mixture will be A plus B. Okay, this is the meaning of these terms. And then total mass of the system is M is equal to Ma plus Mb. Okay, to overall mass, individual masses, summation of individual masses is nothing but overall mass or total mass of a mixture. Then velocity is denoted by Ui for the ith species. Then the units are meters per second. Then for the component A, we will denote it as small u subscript capital A. Then for the component B, we denote it as a small u subscript capital B. Okay, since this is a vector, okay, we have to define it in a vector form for the total mixture for the x, y, z direction. So I am not defining here. In the equations itself, we define that one. Then volume. Okay, volume is denoted by capital U I for the ith species, capital I, where in the I, in every property, I denotes the ith species. It can be A, B, C, D, up to any number it can carry. Okay, any alphabet, any number it can carry. So volume is measured in meter cube or liters. Okay, depends on the particular system of units. Then volume of the component A is denoted by capital V subscript capital A. Then volume of the component B is denoted by capital V subscript capital B. Then total volume is the additive property. So total volume is nothing but volume of A plus volume of B, partial volume. Sum of the partial volumes is equal to total volume. Okay, then molecular weight. Molecular weight we denote with mw, or sometimes it is denoted by capital M subscript I for the ith species. Then its units are kg per kg mole. Then for the component A, we will denote it as M subscript capital A. Then component B, M subscript capital B. So it is not additive property. It needs to be associated with certain composition. Then only we can calculate the average molecular weight. Okay, molecular weight can't be added directly. Ma plus Mb is equal to some M. We can't say like that. So we need to add it with certain composition. That is nothing but a average molecular weight definition. You might have remembered that average molecular weight M average is equal to sigma xi into mi in the CPP course. Okay, therefore we need to carry out that one here. So next property is a mole. For any system, next property is a mole. How we define a mole? Small n I. I is for ith species. Then whose units are mole. Okay, this is small m. Okay, whose units are mole. Then for A component, Na is equal to mass by molecular weight. Okay, moles is equal to mass of A by moles of A is equal to mass of A by molecular weight of A. Then moles of B is equal to mass of B by molecular weight of B. Then total moles is equal to sum of the component moles, Na plus Nb. N is equal to Na plus Nb, which is always equal to small m. Small m, simple small m is nothing but a total mass divided by average molecular weight. Okay. Then next property is the mass concentration. We already defined earlier during the start of this first unit. So mass concentration is denoted by rho I for the ith species, whose units are same as density, kg per meter cube. So mass concentration for the component A is rho A is equal to mass of A, which is Ma, by total volume V. Okay, for the component B, rho B is equal to mass of B, Mb, by total volume V. Okay, therefore the mass of a total mixture is nothing but sum of the mass concentrations of component A and component, which is given here rho A plus rho B, which is also equal to total mass of the component, which is this one Ma plus Mb divided by total volume, this one. Okay, then next property of a system is molar concentration. This is also we already defined. What is the molar concentration? Then it is denoted Okay, I think it is okay now. Yeah, molar composition whose units are mole per meter cube. Then for the molar component of A is moles of A divided by total volume. For the molar component of the concentration of B is Cb is equal to moles of B divided by total volume. Then total concentration is equal to sum of the individual concentration, which is Ca plus Cb. So Ca plus Cb is all also equal to capital N, small n. Small n is the total moles, Na plus Nv divided by total volume, Va plus Vb. So N by V is also called a concentration, which is Ca plus Cb. Then next one is mass fraction. So since we have a mass already, mass concentration we have, so we can define a mass fraction. Fraction is nothing but anything which is present in a fractional amount. Okay, so it will be always less than 1. So we have it only two component system. So mass concentration is already defined. So mass fraction we can define in such a way that it will have no units. So mass fraction is denoted by WGA. So individual mass divided by total mass. Individual mass for the component already we defined is C MA, or otherwise we can take as the mass concentration is equal to rho A divided by capital rho also we can take. Take this one also, rho A divided by rho is also nothing but a mass concentration. Okay, similarly here also for the mass component of B, we can mass fraction, we can say mass fraction is nothing but individual mass is divided by total mass, otherwise individual concentration, mass concentration divided by total mass concentration. Okay, which is equal to rho B by rho. So sum of the mole fractions, sum of the mass fractions is equal to total MA plus MB, which will be cancelled out and we will get only one. Then next one is mole fractions. So we have a molar concentration here. We can define the mole fraction. Okay, mole fraction is denoted by Xi, which has no units. Then Xa is equal to Xa for the component mole fraction of component A in the total overall mixture A plus B is Na divided by N. In this form we can define. Other form is concentration, molar concentration divided by total A, molar concentration of A divided by total molar concentration of a mixture, Ca by C. Similarly, component for the component B, Xb is equal to molar individual moles by total moles we can define. Otherwise, individual concentration by total concentration we can define. So sum of the mole fractions or the sum of the mass fractions is always equal to 1. Okay, then next fluxes. Okay, flux we can denote in two forms. One is with respect to the stationary coordinates and other one is with respect to the arbitrary coordinates. So Ni is flux with respect to the stationary coordinates and Ji is flux with respect to the some arbitrary coordinates. Okay, then whose units are kg per meters per second. So which is denoted for A component is n subscript capital N subscript capital A. Then for component B it is denoted by capital N subscript capital B. Then total flux is nothing but a sum of the individual fluxes. Na plus Nb is nothing but a total flux. So reaction rate we already defined in the mass balance equation. So reaction rate is indicated by minus Ra, because reactants will be consumed in the reaction. So we will put minus sign. So minus Ra, so minus Ri. So it is for ith component. See, whose units are kg per meter cube second. Then for the A component A, we can define it as minus Ra. For component B, it is defined as minus Rb. So here R is equal to minus Ra minus Rb. We can't write like that. So the definitions are very complicated when defining the RS. So you will probably study in the chemical reaction engineering course. And similarly, when we are going through the unit 1, at the end of this unit 1, you may encounter with the mass transfer coefficient. It is similar to the heat transfer coefficient. Okay, we will discuss when this topic will come, whose units are mole per meter square second into some driving force will be there. So we will discuss this later. Okay, these components, these properties, all the properties are for the liquids. Okay, now how it differs when the component A and component B are the or in the gases form, we have to discuss it. Morning we already described all these things in the live board, but now I am just summarizing it. I will give a copy to you also, this one. So just same. If the gases are, if component A and component B are the two components are in gaseous phase, then ideal gas law is applicable. PV is equal to nRT. Pressure into volume is equal to moles into universal gas constant into temperature. So we can define, see, N by V. We can take from this equation N by V. So then it is equal to N by V is equal to P by RT. This one. So P by RT already equal to mole per volume, mole per meter cube, which is also a definition of concentration. So concentration is equal to N by V, we can write. Using the gas law, we can write P by RT. So for the gases composition, mole percentage is equal to volume percentage is equal to pressure percentage, but it is not at all equal to weight percentage. Okay, weight percentage is completely different. So for the gases, this is a valid relationship. When we estimate the mole percentage, we can automatically go for the volume percentage. Any of two quantities will be estimated. One quantity will be estimated. We can put other two quantities equal. Okay, this is applicable only for the gas. Mass, same as the liquid composition, mass is defined kg, ma, mv, mass up to volume, it is same. Usually the concentration of liquids is measured with respect to volume, mole per unit volume, okay, in terms of moles. Whereas for the gases, we usually, it is very convenient to measure pressures, because in the gases, when gas is present in some vessel or some reactor, it will exert some pressure. Usually everywhere when gas is present, it will exert some pressure. So when we calculate the pressure, we automatically, we will have mole percentage and volume percentage in our hand. So we need not to go for this moles and volume calculation is very complicated. Estimation is very complicated. So in terms, we can determine the pressure using the simple pressure gauges. We can just determine what is its pressure, and we can calculate the mole percentage and volume percentage using some basic formulas. Okay, that's why for the gases, pressure definition is very easy. Pressure estimation is very easy. Simply we can connect it through the pipe some pressure gauge, and we will evaluate how much pressure is there. So from the pressure, we can directly calculate how much moles of that gas is present in that particular pipeline, how much volume of that gas is present in that particular pipeline. So this is pressure is measured. Pressure is denoted by capital P, I for the ith component. Then it is measured in the units of Pascal, which is nothing but Newton per meter square, which is nothing but force per unit area, okay, which is the pressure units. Then for the component A, it is denoted as capital P subscript capital A. For the component B, it is denoted as capital P subscript capital B. Then total pressure is nothing but the sum of the partial pressures. Okay, PA and PB are the partial pressures. This law is called Raoult's law. Total pressure is equal to sum of the partial pressures is nothing but a Raoult's law, we call it as. Okay, then molecular weight is same as defined in liquids, and moles is also same as defined in the liquids, and mass concentration, this is also same as defined in liquids. In the definition of molar concentration, as per our liquids are concerned, only we have defined up to here, Na by V. So ideal gas law is applicable. So we already defined Na by N by V is nothing but P by RT. For the component A, see PA by RT we can define. For the component B, we can define concentration is nothing but PB by RT. We can define it. And then next is total concentration. Same as the liquids up to here. See Ca plus Cv, which is equal to N by V. Since N by V is our concentration definition, Pt by RT. Since this is a total concentration is total concentration, so we are defining Pt, nothing but a total pressure. Okay. See here we already defined Pt is equal to total pressure, which is the sum of the partial pressures of component A and component B. So total concentration is equal to Pt by RT. So similarly in the mass fraction is same, since mass remains same in same gases and liquid state. So here it will change. See, in the mole fraction, it will have a no units. Then in the gas phase, we will denote mole fractions with Y. In the liquid phase, we will denote mole fraction with X. So for the component A, Y, small y subscript capital A is equal to individual moles by total moles, same as that liquid we define in the liquid, and concentration, individual concentration divided by total concentration. Up to here, see, it is same as that of liquid, but here pressures will come whenever gas is present in our system. So individual pressure divided by total pressure. Similarly for the component B, small y subscript capital B is equal to NB by individual moles divided by total moles, then individual concentration divided by concentration, total concentration, which is same as that for liquid up to here. Then whenever gas is present, we have to take into account the pressures also, PV by PT, which is partial pressure of B divided by total pressure. So sum of the mole fractions is always equal to 1, or sum of the weight fractions is always equal to 1. Okay. Then fluxes is also same. Na we can denote with Na, and Nb we can denote, and the total flux is nothing but a, which is denoted by capital N. So reaction rate is all same. Okay, this is the notation scheme Okay, we apply usually in our derivations. So if you remember how these conversions are possible, how the units are interchanging, then equations will be very, very, very easy. Otherwise, if you don't remember these formulas, otherwise if you don't remember these units, it is very difficult to derive the final expression. So just go through this file. I will send to you this file. Just go through this file and once again just study the units and conversion, various conversion formulas in this one, so that we can easily derive. So we will derive our first equation now. Morning I was saying about A through non-diffusing B. Already defined, we already defined what is A through non-diffusing B. Library is not working. I think you understood about these units. Anybody has any doubt regarding these notation schemes or units or any conversion? I think it is very easy because you already undergone CPP, Chemical Process Principles course. Anybody can say yes or no?
Yes, sir.
Yeah. Okay. Everything is known to you, Pavani?
Yes, sir. It is okay. We know.
Okay. Yeah. Yeah. We will move on to next one. We will derive equations from now onwards. The live mode. Okay, this is working now. So in the morning we are defining the A through non-diffusing B. I hope you understood that example. NH3 plus A, when we are diffusing this mixture using water, then only NH3 is soluble in water, whereas air will remain um, inert. Okay, it will not diffuse through the water. So we will consider that example as A through non-diffusing B. So we will see A through non-diffusing B. Okay, just read the notes, you will understand what is going on. Heading is steady state molecular diffusion at rest and laminar flow, and the first case among is A through non-diffusing B. All equations are at steady state, your equations. We don't have to study any unsteady state equations as per your syllabus, so it is at only steady state. So we already defined, now we know the relationship between diffusivities. Relationship between not diffusivities, fluxes. Relationship between fluxes is nothing but we already derived this. Ni is equal to nxi plus ji. Okay, this is relationship between fluxes. Okay, this formula is very important in your further courses. So next one is fixed first law of diffusion. These two formulas we use frequently. Fixed law, which is first law. Okay, fixed second law is a big derivation which they will ask separately, but fixed first law and relationship between fluxes are frequently used in this course to derive further equations. So fixed first law, what is it is saying? So ji is directly proportional to minus dou ci by dou z or some dou x or dou y, some saying. Okay, for the component A it is nothing but So proportionality constant we can keep DAB dou CA by dou Z. Okay, see this is we can take this combinedly equation 2. This as equation 2. So this formula, fixed first law of diffusion formula, at the same time the relationship between two fluxes. Okay, this formula is very important for the next uh, around 10 derivations will come. For the around 10 derivations, same formulas, these two formulas we will use frequently. So as per our definition of relationship between diffusivities, we can write, I am writing once again this one, Ni is equal to Nxi plus Ji. So for the component A, we can write this equation for component A. In place of Y, we have to just write A. So which is nothing but Na is equal to N into Xa plus Ja. Okay, if you consider this as equation 3, okay, from equation 2. Equation 2 is fixed first law of diffusion. So fixed first law of diffusion is saying Ja is equal to minus dAb dou Ca by dou Z. So substitute or submit equation 2 in equation 3. So what will happen when we substitute equation 2 in equation 3? Na is equal to Nxa, so plus Ja is there. So instead of in place of Ja, we will substitute minus fixed first law of diffusion, which is minus dAb dou Ca by just wait a second. Yeah, dou Ca by dou Z. Okay, dou Ca by dou Z from the fixed first law of diffusion. Now we are saying what is the definition of A through non-diffusing B. Non-diffusing B. According to this definition, what is the terminology we applied? A is just diffusing into some solvent, okay, which is here in the example we will consider A as NH3. NH3 is going through water, whereas air is remaining constant, air is remaining inert, so it is not at all diffusing. So flux of A is equal to, according to this definition, A through non-diffusing, flux law of A is equal to constant, whereas NB, it is not at all diffusing, so it is remaining constant. So NB is equal to 0. These two are the definitions. Just you have to remember, whenever people say A through non-diffusing means only A is getting diffused, whereas B is remaining constant, means it is not at all diffusing. So flux of A is some constant, it will there, some value will be there, whereas NB is, it is not, since it is not at all diffusing, so we will take NB is equal to 0. So here this is equation 3, then this we consider equation 4. So substitute this Na is equal to constant or NB is equal to 0 in equation 4. Okay, substitute NB is equal to 0 in equation 4. Then what is equation 4? Once again I will write this one. This one is equation 4. This is Na is equal to, see here capital N is there, capital N is there. According to our previously described formula, capital N is nothing but total flux. So which is nothing but, since where there are only two components, which is nothing but Na plus Nb. So the in place of N we have to write Na plus Nb. So in place of Xa, Xa is nothing but Ca by C, Ca by C. You can see, if you have any doubt, you can go through this word file in which it is clearly given. See here, Xa is equal to Ca by C. Okay, at the same time Na is equal to n is equal to, here you can see in this row, n is equal to Na plus Nb. Okay, we have to expand those terms in our equation derivation. So Ca by C, then left out term will be minus Dab. So I'm writing in the bottom minus Dab dou Ca by dou Z. So as per our definition, we have to substitute A through non-diffusing B means Nb is equal to 0. We have to substitute. The left out term will be Na in the LHS side. Similarly, Na plus Nb. So Nb is 0. We have to write only Na. So in place of Xa, we need to write Ca by C. See this one, Ca by C minus Dab dou Ca by dou Z. Okay, this is the case. Then we can just interchange the variables. So we will bring the DAB variable to this side and we will send this NA to the RHS side. So finally what will happen, DAB dou CA by dou Z is equal to NA CA by C minus NA. So now we have to differentiate. Already differential is there. We need to put off this differential with just integral. We need to perform integral operation. So DAB is already there. So dou CA is there. So we have to perform a differential means we need to send one differential to the LHS side, one differential we need to associate with RHS side. So dou Z we will send there, and in place of this we will transfer this to the denominator of LHS. So dou CA by NA NaCa by C minus Na minus Na into this. Okay, some variable is missing, I guess. NaCa by C. Okay, yeah, it is okay. Then we have to send the dou Z to the RHS side, dou Z. Then here you see this is Ca by C. So we need to take common C. Okay, we need to just DAB dou Ca by, so we need to take C common. So when we take C common, so here the variables are C times C, so NaCa will be there minus Na into C will be there, which is dou Z. I'm writing it clearly in the next slide. Just see DAB dou Ca dou Ca. We can just send this to the numerator, we can send. So we can just write it is C here. This C we can write here capital C, which is there in the bottom. See this one we are bringing upside. So dou Ca by NaCa. Na we can take common because it is same. NaCa minus C we can take. So this is in the LHS side is equal to dou Z. Okay, now we have to define the boundary variables. So in our mass transfer, what happens? The concentration, this is initial point, Z is equal to some 0. We are considering this as a Z direction. Then this Z throughout the mass transfer zone, this is some Z is equal to some value Z will be happen. So first what will happen? At origin, Ca1 will be present, then the concentration of initial component will go on decrease as we move to the mass transfer surface. This is called Ca2. Now the boundary condition is when Z is equal to some Z, Ca is equal to Ca2. When Z is equal to 0 at the origin, Ca is equal to Ca1. Okay, this is the boundary conditions. So we need to consider these boundary conditions in our integrals. So we need to set the integral limits. So integral limits are, if you see here, so dou Ca by Na we can take common. So Na is obviously constant. So we can take this outside also, outside of integral, because it is not a variable. So next, so Na Ca minus C, Ca minus C. Then left out term in the RHS side is dou Z. Now we need to fix the limits. So when 0 initially, the z direction is at origin, and finally this direction will go up to z value it will take. So from the initial boundary condition, see, when z is equal to 0, our concentration is Ca1. So that limit we have to substitute here. When z is equal to 0, we have to substitute, we have to put the limit in the our LHS side is Ca1. When z is equal to some z value, the concentration will take the value of Ca2. So this is, we have to, in this way we have to fix the boundary conditions. Remember, in any type of mass transfer, heat transfer, whether it be mechanical unit operations, whether it may be transfer phenomena, more advanced courses like evaluate the limits. Okay, then only it will possible to go the set the limits. Okay, it is not a general mathematics, this is a applied mathematics, so it will be somewhat little tough. Okay, direction that plane is acting, we need to remember everything. Okay, so in this way, this is a simple example. In this way we will take concentrations and according to their plane values, whether it is in origin, whether it is in some in between region, whether it is in complete mass transfer region. Okay, up to this equation. Okay, now this is not moving once again. Yeah, let's see this one. Okay, up to this equation, I hope you understood this one, this equation. So we have to give some equation numbers, it will be better. So this is equation 4. Now we are substituting this one, so we will give this as equation 5, then this as equation 6. Finally we will consider this as 7. Now the limits are this equation as 8. Okay, then equation 8, up to equation 8 we are seeing, lost. Okay, then this is equation 8. So you see here, this is integral, which is looking as, okay, now in the green color I have shown you, this is the integral which is in the form of, you can see, which is in the form of 1 by ax minus b. Bear with me, this is not working like that. Okay, this is another live board. So from there we will continue. That equation is looking, which is in the form of 1 by ax minus b. Okay, first I have to write that equation here. So finally the left out equation will be integral ca1 to ca2. So c dab was there, then dou ca by na is also there, c by na. So ca minus c is equal to integral 0 to z dou c. So once again gone. Okay, now you can see uh, this entire integral or derivative term is in the form of integral 1 by ax minus b. So ax minus b into dx. Okay, now the solution for this is ln mod ax minus b divided by a. This is the solution. So we can just compare these two equations, dx by ax minus b and dou ca by ca minus c. So we can substitute in that one our term, which is ln. So here you can see a is nothing but here 1. Okay, same 1. Then x is ca, then dx is dca, b is c, capital C. Then we can substitute ln ca minus c divided by a is already 1. So we need not to write that one. So the left out term here is c dab by na, c dab by na. So limits are in between ca1 to ca2. In the previous equation, see, we can directly cancel derivative and integral, we can just input the terms z in the LHS RHS side, z in between the limits 0 to z. Now we just have to substitute the limits, that's all. Okay, already solution is available directly using that formula, okay, which we compared. So here you see upper limit minus lower limit. Upper limit is CA2 minus C minus of, now lower limit is CA1 minus C, which is equal to Z minus 0. So in the RHS side. So we already know that formula, ln A minus ln properties ln B is equal to ln A by B. Using the logarithmic or ln properties, we can write ln A by ln A minus ln B. This is in the form of ln A. This is A. So this one is B. So we just have to write in the form of ln A by B. So how can we write this one? So finally the left out terms are C DAB by NA into ln of A by B. So which is A is nothing but CA minus C, CA2 minus C, CA2 minus C divided by CA1 minus C, CA1 minus C. So in the RHS side only Z is there. Okay, this is the equation. Now we can interchange this variable. See, now we can transfer C here, at the same time CA2 here. So we just have to multiply within the ln with minus. So we can just interchange the variable. For the convenience, we can interchange that variable. So how can we can interchange that variable? C into DAB by NA into LN. So here CA2 minus C is there. We have to write C minus CA2. Okay, this will have advantage in the further simplification of the equation. C minus Ca2 divided by, similarly we have to interchange in the denominator also. C minus Ca1 is equal to Z. Okay, then this equation we can write what is Na, we can define what is Na. Then every term we need to transfer there. So NaC, we just have to take this Na to the RHS side and every other term to the LHS side. So Na is equal to CDAB, C into DAB by Z ln C minus Ca2 by C minus Ca1. Okay, this is a very important so derivation. Now we already derived what we are required. Now everything is just simplification. Okay, nothing we have to derive, nothing we have to do. Only just everything is simplify this formula. Okay, this is the end equation. Just we have to simplify this formula. Okay, now see, it is in this formula is for concentration terms. Okay, total concentration we want Ca2, concentration of A at point 2, concentration of A at point 1 we want, concentration, total concentration we want. Similarly here also concentration we want. Okay, these are the terminologies. For example, if the problem is given in mole fractions, then how can we write in the mole fractions? So in order to define that in the mole fraction, so we have to substitute. So we have to convert these concentrations into mole fractions. That's our main criteria. So how can we do that? So divide in the both numerator and denominator, numerator and denominator within ln. Only within ln we have to apply, within ln with C, capital C, which is concentration, total concentration. So when we within ln, only within this term, Okay, within ln means only within this term we have to divide this within ln equation with c. Now we can see Na is equal to C dAB will remain same, C dAB by Z into ln. So ln of C. Within this term we have to divide by C. C minus C divided by C minus Ca2 divided by C whole divided by C by C minus Ca1 divided by C. So C will be cancelled out. So we already know what is Ca2 by C and Ca1 by C. Individual concentration divided by total concentration is nothing but mole fraction. Okay, you can see the old file also. Here C mole fractions is nothing but individual concentration divided by total concentration. Just at plane 1 and plane 2 is different. Okay, only difference is plane 1 and plane 2. So in place of this we can substitute Na is equal to C dAB by Z ln 1 minus XA2. Since these are for the liquids, so X we are writing XA2 by 1 minus XA1. I'm writing clearly. B by Z ln 1 minus XA2 by 1 minus XA1. Okay, this is also a very important formula. I am putting star for these formulas. This is 2 star and this one I am already kept the 1 star. Not moving. Writing that once again. This equation I am writing once again that one, so that we can put a star on that one. So Na is equal to C dAB by Z ln 1 minus XA2 by 1 minus XA1. Okay, this is 2 star. Okay, these two equations are frequently, when we remember these equations, we can use this in the direct problematic questions. We can solve it directly. Okay, otherwise we have to derive. So I am putting the 1 star and 2 star in them. So this is a 1 star star. This equation is very important, and 2 star is also, this is equation is very important. As per your old question papers, they are in the question papers they are giving derivation also, they are giving problems. When they given a problems, then if you remember these equations, it is very easy to substitute data. Okay, then if you give derivation they have given, so you have to derive all these terms. Okay, this is up to equation 2 star. I will stop here today, and tomorrow we will simplify these equations further, and then go for the next, for the gases system. This is for liquid system, and for the next gases system we will derive. Then next, who is coming for the class?
HOD names.
Okay, madam is there. Okay, madam. Good afternoon. Okay, Ravi. Ravi,
Yes, sir.
can you please give me the attendance? Send through WhatsApp.
Yes, sir.
Okay, thank you. Bye.